Today we're going to prove a statement that I'm going to call the Mickey Mouse lemma. Here's what the Mickey Mouse lemma states. Suppose we have a circle and then two more circles that are tangent to it, and then suppose we draw the common tangent line to these two small circles, and that the distance between this point of tangency and this point of tangency is t. And suppose the distance between the point of tangency of these two circles here and of these two circles here is x. Then t can be expressed as x times a coefficient, and the coefficient only depends on the three radii of the three circles. T equals x times the square root of 1 plus the ratio of the radii of the circle and this circle times 1 plus the ratio of the radii of this circle and this circle. Let's see how we can prove the Mickey Mouse lemma. Well, first of all, we know that this center, and this point of tangency lie on a straight line, and also these 3 points lie on a straight line. Suppose that this radius is r2, this radius is r1, this radius is r. Since this line is tangent to both small circles, we know that this angle is 90 degrees and this angle is 90 degrees. And now we can drop a perpendicular line from this point to this line here, such that this now becomes a rectangle. And therefore, this side equals t, and this side equals r2. And now, since this is r1 and this is r2, then this small segment is r1 minus r2. And now we can apply the Pythagorean theorem for this triangle, in which this side is t, this side is r1 minus r2, and let's call this side y. We got that y squared equals r1 minus r2 squared plus t squared written here. Now let's apply the law of cosines for this triangle, where this angle is gamma, this side is r plus r2, this side is r plus r1, and this side is y. From the law of cosines, we get that y squared, written here, equals r plus r1 squared, this side squared, so here, plus r plus r2 squared, which is this side squared, minus 2 times the product of the two sides times the cosine of the angle between the two sides, cosine gamma. Notice that if we apply the law of cosines for this triangle here, we would get r squared plus r squared minus 2 times r times cosine gamma equals x squared. And so we can express cosine of gamma from here, and the cosine of gamma turns out to be 2r squared minus x squared divided by 2r squared. We can cancel out the 2 here with the 2 here. And now let's take this expression and try to simplify it. Let's firstly expand this term, and this term, and see what happens. By expanding this expression, we get this. By expanding this expression, we get this. And by expanding this expression, we get this. Also, this expression can be written as 2 minus x squared divided by r squared. From here we can see that r1 squared and r2 squared cancelled out. Then we get that t squared coming from here equals 2r squared coming from here and here, plus 2r r1 plus 2r r2 coming from here and here, plus 2r1 r2 coming from here, minus, and then we can split the expression in the parentheses here into 2 times r plus r1 r plus r2, and x squared divided by r squared times r plus r1 r plus r2. And now luckily, this whole part of the expression cancels out, because here we have 2r squared cancels out here, 2r times r2 cancels out here, 2r r1 cancels out here, and 2r1 r2 cancels out here, which means that t squared equals this term, which can be written as x squared times, and then distributing 1r here and 1r here, 1 plus r1 divided by r times 1 plus r2 divided by r. And now we can take the square root of both sides, and we get t equals x times the square root of 1 plus r1 divided by r times 1 plus r2 divided by r, which is exactly what we needed to prove. The Mickey Mouse lemma has 2 more variants. This one is when the two circles are not tangent externally but internally to the large circle. And in this case, the expression for t is almost the same. The difference is that we have 2 minus signs instead of 2 plus signs. Here, one of the circles touches externally and the other circle touches internally. In this case, we don't take the common external tangent line to the two circles as we did here and in the first variant we looked at, but instead we take the common internal tangent line and take t to be the length of this segment. Then t equals x times the square root of 1 minus r1 divided by r, so a minus sign corresponding to the internally tangent circle, and times 1 plus r2 divided by r, so a plus that corresponds to the circle that is tangent externally. Here's the optional problem. We have a triangle. This is its circumcircle. It has a radius r, And this here is a circle that touches this line, and this circle here at this point internally. This circle has radius r1. Let the distance from this tangency point to this point be x, and let the distance from this tangency point to this point be y. Then prove that x equals y times the square root of r minus r1 divided by r. And here's the solution. We can consider this point as a circle with zero radius that touches this circle internally. Then this line would be the outer common tangent line between this circle and this infinitely small circle. Hence, we can apply the Mickey Mouse lemma for this circle, and this infinitely small circle. We get that x equals y times the square root of 1 minus one of the radii divided by r times 1 minus the other radius divided by r. The first radius is 0 because this circle has 0 radius, and the other radius is r1, the radius of this circle. Now, this term becomes 1, so it essentially disappears, and this term can be written as r minus r1 divided by r. Therefore, x equals y times the square root of r minus r1 divided by r times 1, which is the same as what we have to prove.